and you just have to make sure that that it doesn't switch. There's no glitches which causes it to react randomly.
That's a neat idea.
Oh, yeah. We are live. Okay.
What you say is in the air.
So the only problem was that I didn't. I used 12 volts from 6 volts from the battery. 12, yeah, 12 volts.
Steppers maybe.
Yeah.
6, yeah.
So I stepped it down to 5,
Right.
and and I didn't have too much safety uh, precautions. So every once in a while the ROM gets fried.
Oh, motor glitch. Yeah, because when the motors are switching, they're throwing all that noise out.
Yeah. So occasionally I just got the ROM burn. But other than that, it seems to work quite well.
That's amazing. That's cool. I like it.
Yeah, I think the logic is that you have when you have. I think what I did was when there's nothing there, it just go forward. If it hits the right switch, it will turn left turn. When it hit the left switch, it's a right turn. Yeah, when both of the switches are on, you just back off.
Right. Yeah.
Yeah,
That's what I do.
I think when both of the switches are on, and when it's backing up, if you kick on the third switch, it will stop.
I got something from YouTube. They say
Okay.
that they're ready for you.
All right. Thank you so much. All right. Let me see. Let me just get this thing. Get the screen to. Oh no, that's. How can I get? Well. Okay. This is good enough. Hello. This is Silicon Valley 4th Interest Group, and I'm CH Ting, and the topic is one-step DNA pattern search. So I just look up my directory and found out that the first time start to talk about this genome, it was last November. So it's almost a whole year. But when I started, I was looking at the genomes, simplest genome, the mitochondria, and say, oh, okay, let me see what's in it, what kind of information do we have in it, and what kind of information we can extract from the DNA and make some sense of it. So the basic thing is that what's information? Okay, we got all the genomes, libraries, gigabytes of ACGT bases. What are the information? What can we expect from these long sequences of DNA? And so the basic idea about information is information are repeated patterns. Whatever you have, what kind of information you receive. If it's random, you can make sure it is random. There's no information in it.
If it's a pattern, it must repeat. If it doesn't repeat, it can't possibly be a pattern.
Well, exactly. Okay. Well, it could be a random pattern and doesn't repeat. Okay. Well, we can argue about.
Every time he chooses a victim that's not like any of the others. Is that a pattern?
Okay. Yeah. So it's a repeated patterns that you want to extract from seemingly a random kind of of data. Okay. So, but information has to take some kind of form. The pattern needs to be certain form. And you see, well, when we look at DNA or the genomes, we know people are pretty sure that there are genes in the DNA in all the genomes. And what we understand about genes are that these patterns code for protein molecules. So this part everybody understand. And when you get a genome and people start to analyze, the first thing they want to know is to find out what kind of proteins, what kind of information in the genome which codes for protein. But when you get to bigger, higher living living things, the genome gets bigger and bigger, and it's getting more complicated. And in the very low life form, the single cell bacteria, there's lots of gene code. There's a little bit of code which they could not find any existing proteins. So they are called hypothetic proteins. They really don't know what they're doing, but it looks like a gene. So they identify things like such. But most of these things, later we call them non-coding DNA. This code does not produce protein, okay? So what's in the non-coding DNA? And the higher the living creature, the more complicated it is, and the more non-coding DNA we can find in the genomes. So generally, in a cell, all these genes are expressed, and the coding DNA supply information to produce messenger RNA. Messenger RNA are used to produce proteins. And transfer RNA. There are lots of DNAs which are actually catalysts or molecules which participate in chemical reactions. And the most significant class of this type of RNA is the transfer RNA. Each transfer RNA is used to add one amino acid to a growing protein molecule. So we have 22, 23 amino acids. So we need 22, 23 of these RNAs. And they also find lots of microRNA. And the microRNA, some of them, a very few of them, people have identified their functions. But most of them, they just exist in the cell. And as far as the non-coding DNA is concerned, mostly they produce, they are expressed into non-coding RNA. So still we just know that the whole sequence of DNA code are copied down into some RNA molecules. But what they do, we don't know. And I think people are starting to understand what they're doing. Okay, so in the non-coding DNA, there are, when I started studying it, I talked to one biology professor, a retired biology professor at University of San Francisco. And he told me, Ting, you got to look at these microRNAs. So I said, yeah, looks like interesting. So I started to look at them. And I think it seems to me like these microRNAs are the crucial carrier of information in genome. So that's a lot of microRNA collected from many, many different species. And so the microRNA seems to form clusters in the non-coding RNA. So that was very inspiring. So I searched the non-coding DNA and found, yeah, there are clusters, lots of clusters. But the collection of non-coding RNA and the collection of microRNA, I believe not complete. They got thousands, tens of thousands of these things. But I still don't think they are complete. So, to search for this information, you can use the existing or reported microRNA and non-coding RNAs. But I think that the scope of this, the coverage of these RNAs are not complete. So the best way to look for this information is in the genomes themselves, in the DNA code. And so I start to look for this microRNA-like thing in the genome and see if I can find anything of interest. And I found that the microRNAs are mostly 20 to 24 base molecules. And I thought that, well, let me just look at 20-bit base patterns in all the DNA that I can find. And so these things, I call them pairs because they are not microRNA, or they are not experimentally determined microRNA molecules. So these are just information that exist in the genome, in the DNA sequences, and I call these 20 base patterns pairs. And these pairs are generally forming clusters in the RNA, and these clusters are called then necklaces. Okay, so I think, or I want to look for information in the genome. And what kind of information I'm looking at? I'm looking at 20 repeated 20 base patterns. Okay, and I hope that these generally, if you find these patterns, you'll find they form clusters in DNA. And these clusters, I think, are useful information, and which are called necklaces. So these are the things that I'm looking in any DNA, any genome. And so I started last month. I was supposed to report on the exhaustive search of pairs. So I want to search for every genome. I want to do a complete search on all the 20 base repeated patterns. And I hope from these patterns I can find necklaces and eventually find out what the necklaces are doing and what the pairs are doing. Yeah. Okay, so I have to identify all pairs, unique and repeated 20 base pattern in all the genomes that I've collected. And I can identify all the necklaces. If they occurred in clusters, I can identify them. And I believe pairs are related to microRNAs. And I also believe the necklaces are related to non-coding RNAs, which are the main mechanism of the function, all the functions in a cell computer. So I did all the search and optimized it. And last month, I want to report that my finding, all the exhaustive search. But this month, I start to say consolidate the code and want to say, well, the code looks still awful. It's not too complicated, but I want to look for ways to simplify it to the point that I give my code a genome file, and it will produce a file which contains the necklaces and pearls. So that was the goal. And I think I achieved that, and I was pretty happy with it. But the code needs to be polished so that I think I probably can hand it to other people. Other people can use it. So this is so I finished all this thing in fourth, and I said, well, yeah. Hong Chao was asking if he said he's learning Python. So I thought, well, okay, I'll try to write it in Python to see how it looks, and then probably Python. It's kind of hard to pass to him all the fourth code, but I need to spend several weeks talking about his code so that he can get used to it and make use of it. But I think Python, if I can get a Python file, I just think, okay, here's the Python file. You go run with it. Oh, I thought I'll rewrite the code in Python. And the simple Python search. So these are all after all the fourth code are done. And I said, well, I just rewrite it in Python to see how it works. So the simple Python code, it's kind of nice because Python code is very simple, and it's very easy to explain. So the first simple Python program, it just sequence through give it text file of genome file. It will just sequence through all 20 base patterns in the genome and locate all the repeated 20 base patterns. So this is the simple Python search. So here, I just do the search. So the genome, I read the entire genome file, and make the genome file kind of it's a text file, okay? So it's basically a text string, and the Python has very nice tools to sequence through, process the strings. And so I just take for I in the range of the entire genome, then I just get the first 20 base pattern. And then I scan through the rest of the genome file and find any repeat pattern, anything that's.
When you read in your first genome,
yes.
You start scanning after that. You understand what I'm saying? You scan after, not.
No. Just I read the genome.
Read the genome's in.
It's a string. Yeah. It's a gigantic string.
Yes. You get 20. The first 20.
Yes, get the first 20.
After that, you start looking for.
No, not after, but one plus.
1 plus. Okay.
Okay. So you start number 1, and you start 0.
Right.
And then you start, when you scan, you start 1 and the rest.
Right. So
and then you move the second, then you find the third. Right. So you don't miss anything.
You look for a match.
If there's a match, you report it, write it out into the export output file.
You're stepping a bit at a time, right?
1 base at a time. 1 base. One base is represented by 1 byte. one character.
20 bases. Then he starts thinking, okay, now I'm going to use this to match, so I'm going to start at one base plus one. All right, let's see if there's a match. Then it keeps moving it down one base at a time.
Yeah, but is the structure of the genome 20 bits per slot?
Not 20 bits, 20 bases. Okay, each base which has a, C, G, or T.
Oh, okay.
Okay, so each base, each base has information-wise, it has 2 bits of information, but data-wise, each base is represented by a character, A, C, or GT, A, C, G, T. So the entire file is actually a text file. Okay, and Python is very good at text files, so I can specify substrings, 20 base substrings, and compare all the 20-bit substrings. So this is the exhaustive search. And you can see for I, repeat from 0 to the end. And for J, it's I plus 1 to the end of the genome. And so you just pick up 20, you pick up a first 20 base pattern and compare with all the patterns in the subsequent string. And if you find any match, just write it out. Okay? So this is the very simple search. It's very nice. It's very easy to explain it, but it's extremely slow. Okay? you can do it only for the simplest, shortest genome file.
You know, you might want to use an FPGA. You understand what I mean? An FPGA.
No. The computer is much more powerful than any FPGA. Okay, the dependence. Okay, so there's no reason to use any hardware. Software is good enough. Okay, it's the tools, the program. Okay.
So question: how does you wrote it in G4 or something like that?
No, this is in Python.
No. But you originally wrote it
in fourth, yes. Mm-hmm.
Was it your fourth or a G4?
The E4th.
E4th,
yeah.
Okay.
Mm-hmm.
32-bit?
32-bit, yeah. Mm-hmm.
So what's the time comparison?
This will come, okay? Okay. Yeah, okay. And this is a more advanced Python search, because Python really has lots of very nice string functions, and I want to take advantage of that. And this search basically it is taking the genome file and make a list of it. Okay. Python has a very nice function which is called set. Okay, if you give set a list, it will search through the entire list, produce another list which has only unique patterns. It will delete all the repeats. So what I want to find are the repeats. Okay, but it has a good function which will delete all the repeats. So what do? You get all the repeats removed, and you subtract that unique list from the original list, and what you are left are all the repeats, right? Okay, so this is what I did. But I don't. The set has a very nice function. The minus the set. When you have two sets, you can add it, you can plus them, and they add both sets. And you can do exclusive or and or the sets. And you can do a minus of two sets, and it will give you all the differences.
That's the nice thing about Python. You can do set
Yes, yes, it's amazing. It's amazing. But what I want are all the repeats. But the function can only give me the unique one. So what I did was here using the remove function. The remove function is that you give a list and you tell it that I want to remove this item. So it will go to the list and remove that one. So what I did was just go through the entire original list of strings and find all the unique ones, and then delete all the unique ones, and you are left with all the repeats. But the repeats can repeat once, twice, 3 times, any number of times. So you still need to delete all these repeats in the non-repeats, right? So what I did was to do another set. After I get the repeats, I just use the set to remove any redundancy. And there I got the non-repeated pattern, unique and non-repeating pattern, right? So it's very nice. And when I write out the file, one of the very kind of interesting thing is that when you find the repeats, the worst thing is that when the genome usually have the repeats, the genes sometimes are repeated in the genome. So you actually have two sequences of the base pairs which are identical. Okay, and this gives you lots of matches because the first one match, the second match, the third match, the whole length of these genes got hit. But these things you have to remove them. Okay, so this is how I remove these very closely spaced patterns, repeat patterns. But I know they are not what I want. They are just two repeated gene sequences in the same genome, but occur at different places. So what I remove is that I just want to compare the address of this string with the last string. If the difference is less than 20, I remove it. Okay, because lots of things are repeated every one, and there are lots of patterns which are repeated every 2 bases, and up to 20. So I just threw them all. I think I probably threw away too many. Okay, but I still have lots of them left. So 20, this threshold of cutting. I will adjust them later if necessary. But at this moment, because I got just too many patterns, I don't know how to handle. So I just eliminate as many of them, and so I can have a smaller file to look at the things that I'm really interested in. So this is fairly optimized as far as Python is concerned. Pretty good code. But tell you the truth, I learned Python for 2 weeks, okay? So I really am not an expert on Python. And I think I need lots of help from the Python experts. Yeah, this is. So I need I need to really somebody who really know Python and its string functions to see what can be done the most efficient way. Okay. Okay. So the advanced Python search Python code is very simple because the rich tool set, especially stream processing tools. It worked very well with small bacteria genomes. It took forever to search E. coli. E. coli has 4.6 megabases, and I turn it on and leave it for a day. Doesn't finish. Wait another day. Doesn't finish. Wait the third day, and finally I'm tired. Okay, I just kill it. It took too long. Yes.
You have to wait a day before you get to see your output.
Yeah. It just for small genomes, it turns out quite a couple minutes or something. But for a big one, it just takes forever.
Like I said, you have to go through the whole genome before you get to see your output.
Yeah, that's right. There's no way around it. Okay, so that's the advanced Python search. Now I'm going to show you the advanced fourth search. Excuse me. So the fourth search, I have worked on it for a year now, right? So I try to do the best I can, and one of the most critical, two of the critical routines are the compare, which compares two strings. Okay, you know the length, you know the location, and you just compare them, the character by character. So this will return a flag. If it's 0, it matches, the two string matches. If it is -1, first string is smaller than second string.
Collating sequence.
Yeah, collating sequence. Okay, so that's the compare, and the look, which is also I think is a Python function, and it just in a long string, you look for a pattern, a short pattern, and you give the long string the length of it, and you give it a small pattern and the length of it, and you will search and return an address or an offset into the big string. And if it doesn't find it, doesn't have a match pattern, it will return a 0. So that's the function I want to code most efficiently. So this is the optimized compare. So the critical part is this instruction, compare SB. So it compares string, compare byte string, okay? And it repeats itself with a repeat prefix. You just repeat the search until it find the compare, it find a mismatch, and it will stop. Okay, so it would do all these things, and you just jump. After it stops searching, it does a condition. It will tell you whether it's bigger, whether it's less, or whether the two string is equal. So this compare string byte is the most efficient instruction to do string search, and you cannot do any better with an Intel type microprocessor. So this is the fastest, and use this instruction. You can optimize compare, and you can also optimize look. So compare and look, these are very similar, but compare, you know both strings, and you do the comparison. Look is that you have a big string, you have a small string, and you look for this small string in a big string. But the code is almost identical. It's using the compare, the same thing. Okay, so with these two functions optimized, you can build all the search algorithm on top of it. But I tried this dumb search that you search everything and you do this. It's the compare, the number of compare you have to do is n squared. so this is okay with small genomes, but when the genome gets larger and larger, the search time goes into the square of the length, and it's just unbearable. And so in my most recent version, I break the genome into 496 threads. Okay, and each thread is all the patterns which starts with a unique 6-base pattern. So I just use 6 AAAAAA and AAAAAC and AAAAAG, okay, and just start all of them and search through the entire file for this particular pattern. And I only have to remember I just use the run length coding to locate all these patterns. So it is the first thing is I search for the 6 A's and the next 6 A's and next 6 A's. And I only have to remember the length, the run length between the two patterns. So this was a way of compressing. And generally, I think it's called run length coding. So you just, from one pattern to the next pattern, you just remember the difference, the distance of this thing, and you can get all the information there, and then you can do all the search. So I break up the genome into 496 threads, and to look for repeated pattern, you only have to look at a single thread, because if you have a pattern which starts with 6 A's, all the repeating patterns will be in the same thread. So your search time is reduced by a factor of 4096. Okay, so this is the advanced search, and I only have when I first did it, the data file, the run length is still very big. So I thought, well, I need to compress it. So I use run length coding and to compress this file. But later I found, well, it's really not necessary, because this data really doesn't have to be written out. I have the data, I can process them in the same code. Okay, so this will save lots of time and lots of grief in dealing with intermediate files. I have to save the links. I have the threads, and I also have links. So these files need to be saved. But finally, I realized that I don't have to get all the threads before I do the processing. I get one thread, and I get all the information to process all the patterns with this unique 6-base pattern. So when I identify one thread, I can just go ahead and find all the repeat pattern in this thread. And once I found all the thread, I don't have to save it. Okay, I just repeat the next pattern, find next thread, store them in the same place, and do the same search. Okay, so each thread can be processed right after it's produced, so you don't have to wait until all the threads are produced. And the run length coding is not necessary. You just have to remember the address of each point where the 6-base pattern is repeated. So this saves a lot of work, lots of code, and the searching is greatly accelerated. I'm very happy with that. So I just want to show you the code. Just want to explain it. So the code are separated into the last six words. And scan look is using this look function to scan for the next six base pattern. Okay, so scan look just look through the entire thread. Now, I mean, look through entire genome and find the particular 6 base pattern, and then record the address of each occurrence. And this occurrence is a list of addresses. And from these addresses, I can do the comparison. So the scan look just go out and produce an address file, which identifies all the locations where the particular 6 base pattern occurred. Okay, and the address is left in pad, so I didn't didn't do any array or anything, just save it in pad, which can be reused as many times as you want. So this one just scan through the entire genome, and I store the 6 base pattern in this array called source, and then compared with the rest of the threads. Okay, so you just you go through the thread. Not going through. I'm producing the thread. Okay, I'm going through the entire file and find the 6 base patterns and save the addresses in a list. Once I have that list, I can do the comparison. And the compare, I use the pass 1 and pass 2. Pass 1 and pass 2 are almost identical, but I couldn't find a better way to combine them. So the pass 1 scans a thread and write out the first matching pattern. So if I find the first matching pattern, I just quit. Okay, and this way I can get the first match. And pass 2 scans the thread, write out the rest of the pattern. So these are almost identical thing and can be combined into one code, but I tried many things and nothing worked out. So I just repeated the code, just comment out the stop. Okay. And then scan pass would just call pass 1 and pass 2 to write out all the matching pattern. So to get the first match is very easy. To get the rest of the match is rather easy. But to get the first and the rest, I still haven't found a good way to do it. So this is the pass 1. It goes out and to do the match, okay? And when you find the first match, it will just exit. And this way you going through the thread and find only the first match, okay? And then the pass 2, do exactly the same thing, but it just write out all the patterns. Because when you see the problem is that you have the pattern you want to search, and you search through it. You won't get all the patterns that's matched. But you also want to record this first pattern, okay? And if you record this pattern unconditionally, it may not have anything following, okay? But if you find out the next one which is valid, you write it out. But if you want to write this one out as well, you have to do it for everything else. So that so I think it's just write the code twice, okay? And once you get the first one, and the second time you get the rest. So this one just combine, initialize everything, and because all the data are stored in pad, you start from the pad and go down the list, and do the pass 1, and then do the pass 2, and all the matching patterns are written out, and you can return and do the next one. Okay, the next one, do code, just combine everything and start out the genome file and do the first do the find out or look up all the build a thread, okay, and do the pass 1 search and do the pass 2 search. So the decode, it goes out to the scan look, and then get the thread and do the 2 scans to get all the matching patterns. And the matches, you have to open up a file. You have to open up an output file, write only, and then to go through this. When you write anything out, they go into the output file. And so this one, the final code is this matches would get one file, the source file, open both the source file and the output file, and then do all the processing, write it out, and finally close all the input file and the output file, and then you are ready for the next genome. So here, the however many genomes you want to do, just write it out that way, and it's pretty easy. But the Python has a better string processing property, so that I just give it a name of the file, and I attach the rest of the name, and would do the input file, and it would generate the output file with only one file name. I think I can do it in Ford, but
that might be something that could be added to Ford.
oh yeah. Definitely.
Yeah.
It's just that the effort that I have doesn't automate all these things.
Right.
So I have to open the file with all the parameters.
Yes.
And then all the input file, output file, I have to have a long list of things to specify. But okay, that's what the fourth people do. Okay, so here are a list of the single cell bacterial genomes that I have analyzed. Okay. And I think these are for the professional who can read Latin. And I just simplify them into small ones that I can understand. So the genome, I just listed the size of the genome. The first two, these are not independently living bacteria. They have to exist in a host. So it relies upon the host to supply lots of proteins for them. These equators and genitarian, these are freestanding bacteria. They can live by themselves, but of course they seek for the most best environment for their existence, and most of the time it's human body. Okay, and acetyl, yeah,
coli and these lots of other.
yeah. They are mutually beneficial, and this is the lactase, the bacteria which digest lactose and for milk, to digest milk, and I think it is also good for. I did it because I love what the Germans do with their cabbage.
Oh, coleslaw.
Uh,
Sauerkraut. That's it. Yeah. Yeah.
yeah, yeah.
Sauerkraut.
Yeah, sauerkraut. Okay, sauerkraut, and we Chinese do the same thing. Okay, but we use cabbage and fermented and this.
Cheese with Koreans.
Yeah. So for that reason I do it. But this one has 2 million bases, and E. coli has 4.6 million. So these are good things for me to test to see how well my program work, my search algorithm work.
I think that to have room for extensive end user license agreement.
Okay, here's the benchmark. So that liars do benchmark, right? So the purpose of the benchmark, or the purpose of doing the Python, is to show how bad Python is, right? So this is to show you how bad the Python.
You understand why it's so slow. There's a Python engine. That's bytecode. Okay. And that's where it's bogged down.
Yeah.
Okay,
No.
the first thing it's got to do is compile .py to .pyc. It takes that and runs it in this Python engine. Okay.
Yeah.
Forth doesn't have that.
Yes. I use the pending, the compare stream byte. That's the best way, the fastest way to do anything.
You can incorporate that into a fourth word. You can make what's called a super instruction.
Yeah. Well, I got the super instruction. Right? So here, I just listed with all the bacteria. You see how big they are, and how much time I need to analyze them in forth. So this one for 4.6 million bases, it took me 25 minutes to finish it. And you see here, it took forever. Hour. It's an hour and minutes. Okay. So you can see how bad it is. But I'm a liar. So I think it doesn't count. Okay. Because I'm not an expert on Python. If given this problem to an expert Python programmer, I'm sure he'll come out with something much better. Okay, so this is I just present here. It's about a 60 times advantage in forth.
Yeah, one of the things, because I noticed that in your Python program that you read the whole genome in.
Yes, why not?
Well, I was going to say, when you go to bigger and bigger genomes, you may want to use something called a memory map, where you bring in a portion of it, okay, into memory. Then you can operate on that. And then when you get to the end, you just bring in another one. Then bring in another one.
Sure. Why not?
So that you get that, but it's a lot quicker. Also, using, because I've done this with GUI, such that this thing is running in the background. So every time you get a match, you can say, you can bring that to the GUI and say, found a match, found another match. Here's what it is. You can kind of keep a list of those. Yeah. Because see, then you can get an idea in real time of what's going on.
Yeah.
Okay.
Yeah, I think there's infinite ways of killing a bird. Okay, and I think I found the best way to kill a bird this way, and any other way, I don't know, but.
It's a lot of praise.
Yes. I don't. It's not fair. Okay, at this point. Because I'm not a Python expert, I think. You see, the Python code is very clean, very short, very clean, and that's the advantage. Once you can express your thought that way, implement it. You can. It took me a year. Yeah, it took me a year to get the fourth code optimized. Okay, so I think if a good Python program took that much time, he will come up with something pretty good. So I got lots of pairs. So this repeated pattern, this is one of the problem. Huge number of repeat patterns in consecutive locations caused by duplicate genes. If you have two genes duplicate, then you can get that many repeats into your file. So you have to find out ways to eliminate them. And generally, I get a file, 200 kilobytes or 200 megabytes or something huge. But if you just delete all these things, it reduces itself to a couple thousand bytes. So that was manageable. And only those bases which are outside of the repeated genes are identified as pairs. And pairs, you find all the pairs. You have to give them a unique ID because 20-bit patterns are really hard to read. Okay, if you sort them out, you can probably see things are ordered. You can understand them better. But if they are occurred by their natural positions, it's very hard to know whether two pairs are the same. So to list out the pairs in a necklace, you need to find a way to identify these pairs with much shorter IDs. And then with these IDs, you can look for pairs, look for necklaces in the bacteria, and preferably if you get all the necklaces, you want to merge the file with the annotation, the bacteria annotation, so that people have already identified lots of proteins in it, and they have identified them. And this information are readily available. You can extract this information and then merge them in my data file, so you can see, there's a whole bunch of genes, and there's a bunch of pairs, and then a whole bunch of lots of other genes, and then some necklaces. So these are very useful things for biochemists to look at and see if they make sense. So lots of pairs appear in clusters. And clusters of consecutive pairs are called necklaces. Necklaces are often found in non-coding DNA and non-coding RNA. But I found that lots of these necklaces are in the coding area. So this gives you something to think about. Make the geneticists to think about that their assignment of proteins or genes may not be correct. Okay, so it's another way to look at the genome. And I think necklaces probably represent high-level functions in a cell computer. That's my belief. And here I can show you a little bit of the code or the necklaces in the E. coli. So this part is original analysis. So with all the all addresses and the gene assignments. Okay. And this is the per assignment, and it's I think a very important thing is to record the distance between this pair and the last pair, and this shows the distance between them. And I want to find out the necklaces which are close close by. Okay, so here are the many of the necklaces I can identify. Okay, and the spreadsheet is really nice. So I go through this column and find out the necklaces and copy them into another column and another column, so I can see the necklaces horizontally rather than vertically. The file is just too big, too long to make any sense of it. Okay, so in my cell computer model, pairs and microRNAs are instructions. Okay, and protein coding genes are primitive instructions. They actually do things which produce proteins. But necklaces are high-level instructions with lists of pairs. So I think, I believe this is how genomes, the non-coding genomes are actually coded and it's enforced. Okay?
They're not creating proteins, they're manipulating proteins.
Right. And to manipulate these, manipulate these low-level primitives, the best way is nested lists. So you can do functions, and you can do high-level functions with another list, and then.
Not to mention having proteins that manipulate proteins.
No, proteins don't manipulate protein,
Okay.
but it's the cell machinery which produces protein.
Right.
Okay, which may manipulate protein, cut them off and connect them together, but that's the at another level. Okay.
I have a comment.
Yeah.
Okay.
Make it brief.
Real quick, okay. x86 and ARM have what are called vector instructions.
Uh-huh.
Okay, and what you do is you're able to pass vectors, which can do very primitive add, subtract, multiply, divide,
Okay.
XOR, all this stuff. This might be the thing that could speed up your stuff. And the reason I say that is I read a paper by Bernd Payson who did G-Forth, and he's considering implementing that into G-Forth, which I would think would be a great thing for you guys because.
This sounds so exciting. You can tell them all about it on the way to lunch.
Yes. Okay. All right. Okay. Thank you very much. See you in the afternoon.
I have 2 comments.
Yeah.
So
No. Tell them on the way to lunch.